All right, welcome back to more cognition. Up until now, we have done a lot of work showing off different ways, different routes, right? We had the physical symbol system hypothesis, the idea that, the mind is this sort of neat symbolic structure that moves things around. But then we've also looked at the neural modeling approach, which is, if we can model one individual cell and the way that it works, and we can see what we can build out of that, how it comes to resemble more of a human processor. So now we're talking about a different approach. This is an interesting take. It's a powerful theory in general terms. And there's been a movement to bring it in tighter to studying the human cognitive system. So, dynamical systems theory. What are we on about? And again, to recap, the idea is, our brains are capable of processing information. It seems very clear. And in some ways, it's highly specialized. In other ways, it's a very general information processor. And like we just said, there's two different ways that we've already talked about. The physical symbol system is the idea that we can transform information using internal languages and abstract symbols. And then the other option is the neural networks approach that we've talked about, where we're saying, hey, low-level neural activation patterns are what we can really build the rest of the mind out of and map our inputs to outputs, move information around in this very low-level pipeline sort of way. These are both valid. They sort of tackle different levels of explanation, right? You could imagine piecing together neural networks to make sense of physical symbol processes, right? But there's a different category of approach here. Dynamical systems theory is a way of looking at all of perception, action, the tasks that we do, the environments in which we live, and how our physical bodies all work together as this interconnected, interdependent system. So it's stepping away from questions about representations, right? What form does a symbol take in my mind? What are the neural patterns that represent a symbol, right? And back into just what can we observe? What kinds of relationships between all of these things, our perceptual processes, are the tasks that we do, the actions we take in those tasks in the environment, and our bodies as the intermediary. How do we connect all of those with observable things and a whole lot of math? So it echoes of behaviorism, right? It's stepping aside from the idea that we should be focused very deeply on what are the exact processes within the mind, and stepping back and saying, okay, how can we relate this in terms of observable behaviors, not just of the individual person, like in the old behaviorism approach, but of the whole kit and caboodle, right? The whole big mess that is us interacting in our environments. So, what is a dynamical system? Any system that evolves over time in a law-governed way or rule-governed way. Examples of these. The solar system. Think about the solar system, right? We know that there are 8 to 9 planets, depending on what when you went to elementary school. There's a number of planets. There's an asteroid belt, all these kinds of things, right? And they're moving around the sun. And they're moving in time, in predictable ways, right? Predictable meaning law-governed ways. We have an ability to predict how Venus will travel over the next year, decade, million years, honestly, because it's very predictable. It's very law-governed, the way that things move in our solar system. So that's a strong example. But there are simpler examples. Pendulums, right? That's a thing that swings back and forth in this, swinging is governed by the laws of gravity and the ways of angular momentum and all that, And it's a way of saying, okay, can I make sense of how this thing is supposed to evolve. Is there a pattern to the way that the pendulum changes its position? And can I pull that pattern out, right? Trying to make sense of a pendulum is the same process as trying to make sense of the solar system. It's just about finding the rules, the things that guide the overall dynamics of this system. I also mentioned filling a bathtub, train patterns. If you were ever in the city, the way birds migrate, or even how they just move through the air. Point being that the human cognitive system is no exception, right? We know it's a very complex, interlocking, intermingling thing, but it's yet another system that may have certain strong rules that are observable. And to make it even clearer, the Turing machine and neural networks, these are also dynamical systems. They just, a neural network, if I feed in these patterns of activation, and then we follow how the neural activations fire, well, then we know the rules, right? The rules of a neural network, the laws of a neural network are the properties of, the weights and how we combine signals to create the overall pattern, right? And it's predictable because it moves in a law-governed way, right? So, what are we on about, though? This is, if those are the same kind of thing, why are we talking about it as this is different, right? This is, these are just more neural networks. The main idea is that you can study all dynamical systems using the same sort of mathematical laws and relationships that you might find in complex physics. We'll show some later about how this, you can find curves and attractors and things like that, setting up systems that move toward one another. That'll make more sense as we move. But the idea being that you're trying to find sort of the mathematical folds of, where are all of the local minima and local maxima that help us make sense of how systems tend to fall into place. So in cognitive science, dynamical systems typically focus on this sort of structure. So we don't talk about symbols or chunks or even data, and we're not talking about algorithms or processes. What we're talking about is things that are observable inside these three different categories. Things that are observable within the environment, things that are observable within the organism itself, so our bodies and ourselves, and things that are observable at the task state. So let's think, and we talk about the constraints of these different things, right? My body constrains me in one way, my environment constrains me in another, and the tasks I'm trying to achieve constrain me in yet a third way, right? So let's talk about task constraints. What are we actually doing? What is the thing that we're trying to achieve? This might, this has to do very much with whatever our current goals are. Any task has some kind of goals and actions you can take within that task. So think about catching a ball, right? Moving your arm is pretty important to that task. That's both a good action, it gets you closer to your end goal, and is valid. Kicking, on the other hand, it's a valid action. You can do that. I'm able to move my body in such a way that works, but it's not very useful. So you can see how the task constraints show us, there's sort of the moving of the arm can also be invalid. It's always valid, but it can be not useful. Like if you move your arm behind your back while you're trying to catch a ball. This shows that there's sort of a null space there's a lot of actions that you can actually take for a given task, but only a handful of them are meaningful for the task. So that's how the task can constrain what we're doing. Organism constraints have to do with what are my bodily features, right? What if I don't have any arms and I'm trying to catch a ball? I'm going to have to do a very different strategy, maybe something involving my neck and my shoulder or something like that, or more likely I'm just not going to play the ball catching task at all. But you can see how the abilities of my body constrain my space of actions. So, you know, how toned are my muscles? Am I missing a limb? Do I have good vision? Is my balance impaired? You know, what's going on with my mood? Hungry, sleepy, dopey? What am I? What's my current state, and how does that impact how I can behave? And then finally, environmental constraints are more about. So what we've talked about, the task is like this specific thing I'm trying to achieve, and my body and other internal states are the organism constraints. The environment constrains additional things. So if I'm trying to catch a ball in an open field versus in my bedroom, well, that constrains how many steps I can take to try to catch this ball. How much space do I have? You know, what's the temperature? Is it too cold outside to be doing this dang thing? Or perhaps too hot, right? If my task involves trying to understand some kind of spoken word, is there too much noise around me? Is the environment status interfering with how I behave and thus constraining me? So, take those together, and the big idea is that we are systems that are embedded in our environments. We are connected. All of our behavior is not just driven by some internal regulator, but it's driven by other factors, things about our bodies and things about the environment around us. So, and this is a key thing for dynamical systems. These things are inextricably linked. You can't talk about one without talking about the rest. So the reason this ends up being a separate approach from what we've talked about so far is that it's not saying, it's talking less about, hey, what are the features of the mind, and more saying the mind is just one of the elements that are always interacting in the complex system of our lives. And so we need to focus more on those interactions to understand our human behavior and the way we perceive and process the environment, rather than just focusing on the brain and the jar, you know. So in the dynamical systems approach, we're trying to model these linked elements together. So you're trying to say, okay, given all these constraints, given the task constraints and what my goals are, but my organism constraints and the constraints of the environment, what's the most likely sort of actions, or perhaps the most useful sorts of actions that we can actually take, given our constraints. In dynamical systems models, they get heavy in math. They involve calculus, difference equations or differential equations, because it's trying to analyze how the system evolves over time. And this is the same kinds of things you'd find in physics. Now, we're not gonna talk about Diffie-Q, but in basic terms, first order is you can capture the relationship of all these different variables and all these different behaviors that we might observe in the world at any given moment. But then it scales up to second order. You can see how those moments evolve over time. So this leads to the idea of state spaces. We talked about problem spaces, right? This was the idea of, like, you know, what is the shortest path to winning at tic-tac-toe? I have to consider all the possible moves that my opponents can make and I can make. You know, I navigate the problem space using heuristics and good rules and stuff. But this is more for continuous behaviors. So many of our behaviors are more continuous. How do I walk? How do I maneuver myself? And even speaking can be thought of as continuous in many ways. So given whatever variables we're interested in, what are all the possible valid states? Very similar to what we talked about with problem spaces, right? A problem space had some invalid actions. For instance, in the fox, carry the fox across the water, carry the wolf across the water with the chickens or whatever it was, you had actions you could technically take, but they would end up in an immediate loss, so they would be considered invalid. The same idea here, but we're talking about a broader space of possible states of these, you know, these continuous variables. So think about balancing. If I am going to balance on one leg, on one foot, think about where my center of mass is and how my forward momentum might affect that. What are the possible states? Well, there's a state where my center of mass is far, far, far ahead, like forward in space, compared to my point of anchoring my foot. That's not an especially valid state, because it's going to lead to me toppling over. You can see how there's sort of an attractor of the ground wants me to fall to it. Not to give it a personality, just the ground is the fail state because of gravity. So the possible states of me maintaining my balance involve my center of mass being close above my foot, my pod. So there's only a handful of states in which I can actually maintain my balance. Getting shoved out of those states will cause me to fall. But but within those states, I can make minute adjustments to my body. So ends up being this space of my center of mass can deviate a bit from where my foot is located in vertical position, or horizontal position, but not too far. Otherwise, the system cascades and I fall to the ground. So let's look at another example of this, a pendulum. Here is the possible state space of a pendulum. It's going to wind back and forth left to right, right? This pendulum isn't really losing much speed, but you can see at the top is an actual pendulum that might swing around, right? But then the bottom is charting where that pendulum's end effector is going to be. The big part of the pendulum, the sphere, the orb, whatever, the circle. So it's going to wave back and forth over time, right? And that has this sort of sinusoidal pattern you see. That's the state space. But there's other things that we can calculate about this state space, right? So this is the raw data that we can observe. But we can also observe more complicated states. So you can calculate the velocity. This is why I brought up calculus. You can also make sense of the state space in terms of the velocity. So this is a 3D plot. It's a little bit hard to see what's happening here. Left to right is still the pendulum's its position. It's hard to imagine it, but if we go back, this is, you see the negative p to plus p and then over time, right? Well, that graph has been laid down, so the t is still there, but now we're also calculating what's the velocity like. And we're seeing, again, this very predictable pattern of the state space. It's still waving back and forth along the positional, but it's also moving up and down in the velocity. It's starting out moving fast to the left, and then that velocity shrinks, fast to the right, velocity shrinks. The velocity moves up and down, and it creates a more complex state space that we can talk about in terms of, okay, these seem to be governed by certain laws. This is a very regular pattern the pendulum has. That's great. A pendulum is a simple example, one that is very easy to analyze, but being able to see that this is a set of patterns, and some of the data here is not quite obvious. We don't necessarily keep track of velocity at every time, but we can calculate it. So that's where we ramp up into being able to observe more things about the environment and the things moving in it. We can then perform larger scale mathematical explorations of that data. So state spaces, they help us see the possible states, but they also let us see how they change over time. So adding that velocity element to the pendulum state space helps us predict, oh, it's moving at this speed, I can predict the velocity, I can predict the position, right? So another concept in this type of analysis, the dynamical systems, is called basins of attraction. So we talked before about local minima and local maxima, right? We talked about them in terms of like trying to search and getting stuck. And it's a similar concept here, but it's more sort of real time than like in problem solving. So this is the idea that there are basins of attraction down which we might roll. It's tricky to think about that in terms of like how I navigate my daily operations, but losing your balance is a good example. Like I said before, there are certain spaces in my, where is my center of mass relative to my footing, right? Where I'm going to fall. If I'm standing mostly above the footing, I have lots of ability to stay upright. But as my system lets me get a little closer to these basins of attraction, i.e., the entire circle around me, wherein my center of mass is too far from the middle, would be a basin of attraction in which I would fall, right? And to get myself back up, put a lot of effort into all that, right? So, yeah, basins of attraction are a useful idea. You can think about them on a higher scale by maybe thinking about how is it that I navigate my daily life, right? To some extent, if you are having a pretty stressful week, you might end up eating something you're not supposed to, or you might end up, engaging in some blow off steam type behaviors, right? Now, it's weird to think about that as though I have no say in it and I have no volition, but you can see how the variables kind of fit together, right? When your system becomes destabilized, you might need to fall back on other patterns that you might not prefer. So this is a useful idea. It helps you to understand more of the complex interaction of your life with your environment rather than just focusing on the mind as the sort of the hallowed, halls of the mind. So, yeah, dynamical systems. Overall, the idea is that we should be looking at the synergies between all these interrelated systems and trying to understand those synergies more so than trying to understand one piece of them explicitly. So the idea is we want to look at measurable and meaningful variables. For the example of me teetering and tottering over my center of mass, that kind of makes sense. It's the idea of what can I do to affect my center of mass while I'm trying to balance. And that center of mass being so key to my task of standing upright that it's a very good variable to try and make sense of the way my brain and system are handling it. So to do that, we need to watch and model how these things evolve together, how they change over time, how they impact each other. And, with the pendulum, that's easy to see. There's only two things. It's a pendulum and gravity, right? But with a human system interacting with many other human systems, that's a lot to look out for. So there's a lot of work to do to make sure we can grab variables that are meaningful and, stop observing some of the other ones. And so the idea is it's less about how exactly we are processing information from the world and more about how we perceive the world in service of how we behave in the world. So kind of finding that the path between, inferring the path between processing information, perceptual processing and motor actions. So again, there's a whole field of cognitive science called perception and action, where they don't really talk deeply about the internal representations, the internal machinations. It's more about saying, given what we see in the dynamics of how the perceptual field works and how our motor actions occur, we can come up with a stronger theory. Then neurons can take over and explain how that works, right? So it's sort of anchoring the discussion on both ends by saying, what must this cognition be doing? And so how can we think of this in terms of cognition? I just talked about it at the higher level. Let's look at a very simple example. Okay, think about steam engines. Steam engines produce big blasts of steam to move the machinery around, right? So I boil up steam using heat, using coal. I then move some big wheel, called a flywheel typically, and that motion of me moving the wheel with the blast of steam creates rotational energy, and that can be useful for all kinds of reasons. Like train wheels is a simple one, but you can convert rotational energy into electrical energy using a generator, right? So we just contain these little explosions, and here's the problem though. if you just let this run and you didn't have a way of carefully and dynamically limiting the amount of steam you let through, you would just blow up the flywheel and the train and everything. There needs to be some mechanism that regulates how that steam is released. Let's try that computationally first, according to our old model, a physical symbol system hypothesis. A computational governor might do this: measure the speed of the flywheel, right, and keep track of that information. Compare that to the actual speed that you see against some desired speed you have set. So if those two are equal, fine. We don't have to take any action, return to step one. If not, if those two aren't equal, then you might need to measure the current steam pressure, calculate the alteration of how I'm going to move and change the gaskets and the amount of heat being added and all that, and adjust the throttle and change all these behaviors. Finally, you make that throttle adjustment and you go back to waiting to see, is this thing working? This is fine. This works. This is the computational approach. And there are ways to do this pretty quickly, I would imagine. A computer could certainly do it, a modern one. But looking way back, they didn't have computers. They didn't have onboard computing in the steam engines of the past. How did they achieve this without something that was able to, continuously maintain this like view of the whole system? They did it using the Watt governor. So the Watt governor works kind of like this. It's an interconnected system, and it's continuously and automatically and instantaneously adjusting to the appropriate level of steam. And it does this without any monitoring. It doesn't have any system that overlooks what's happening. It's just the way that these systems interact causes this behavior to self-regulate. The quick example is, imagine if we just have the valve opening that allows steam pressure through to the flywheel and none of the bottom stuff. So if that's the case, then the valve opening has no way to get any information back from the system, and it just blasts the flywheel until it explodes, right? But what we can do is we can have the flywheel give some of its momentum, some of its energy to these spindle arms that will move in accordance to how much pressure the flywheel is getting. And those arms are connected to a system that will then close the valve. The more pressure goes up on the flywheel, the tighter the valve gets because of the spindle arms. So now what you have is a valve that's just blasting steam, but it's getting self-limited because of the dynamics of the pressure affecting the flywheel and the spindle, the arms then choking the valve a bit. So these systems all just automatically constrain one another to produce this intelligent regulation. That we saw in the computational governor, the idea of, this is how you would have to observe and maintain, keep vigilance on this system to make sure it works properly. But the Watt governor does all of that just by exploiting the rules of physics in an intelligent way. So how do we think about that in real cognition? The Watt governor shows you can construct interconnected systems that seem to be processing information, right? They rely on the amount of pressure, right? And the rotational energy of the flywheel and all that stuff. But they don't need abstract computation. They're straightforward. They're clear. It's clear how we would deal with that. So it's not clear that this method, this approach explains all behavior, but it does give us a stronger way of thinking about behavior in service of the world and on our interactions in it, because there are so many different constraining systems all interacting together. So whatever the mind is doing and however it's constructed and whatever it may be, whatever neurons may be in there, it is still part of this broader system that we can talk about in terms of the way that certain synergies are exploitable and more, sort of the easiest path. So let's talk about catching a ball. This can help to illustrate. If you want to catch a solid hit, right? The ball is high, it's gone up, and we're way in the outfield, and it's our time to shine, right? So we need to run both far and fast to be able to get to where this ball is going to be. But where do we stop? When do we slow down? How do we make these decisions about how we move in the environment to get there? So in the information processing world, we might do something like the computational governor. We would say, oh, I'm going to have to process this ball's movement. I'm going to have to infer its trajectory arc, and try to get velocity information from vision. I'm going to try to do some complicated physics and solve its landing position. Then I'm going to have to figure out my motor plan to get there in real time and execute it all at the same time, right? That's a whole heck of a lot. Now, we did talk about how neurons can solve a whole lot of different problems, and in fact, they could get us pretty close to some of these things happening rapidly. But this also has this problem of it's you have to do it all up front, right? You're intermingling this like need for constant action immediately with this need to sort of plan exactly where you're going at the same time. So there is a simpler solution to this, and it jibes really well with the way that we can talk about our motion in this task as part of a dynamical system. And it has to do with the way our retina can process the world. So this is just a strange physical fact about the way that things move from first person's perspective on our retinas. But here's the thing. If you move your body in such a way, well, hey, pause. Let's think about this. The ball is moving up and down in the air, right? If I hold still, it's going to be moving faster as it rises. It's going to slow down to a stop, and then it'll immediately turn around and start moving faster and faster and faster. If you move your body in a way that you actually keep the velocity of the ball's pattern on your retina constant, so it just goes up and down, you have to move pretty quickly and in a particular way to do that. But it is a physical fact of the world and the way that just geometry works from a first-person perspective that you will end up in a position to catch the ball. You will. It's just a rule of how that works. So something like this. I think this presentation software did a little bit of smoothing there, but that pattern is not something you might not know that you use this, but it is something that is a guaranteed solution to the task. So as you're running, you can just maneuver yourself in such a way. You can adjust your current speed and orientation and bearing and everything to try to capture this pattern, this slow, constant up and down motion of the ball in your vision. So that's powerful. That's a very simple thing that I can keep an easy lock on. Think about the Watt governor. If I move myself and constrain my actions in such a way that exploit this very simple piece of the geometry of the world, then I can solve the problem without any long-term planning, without any calculating complex trajectories. I can just learn how to keep the ball in motion in my eyes. There's another interesting piece here is that another simple feature of the geometry is that the rate of expansion, so how quickly the ball is getting larger on your retina, actually perfectly relates to time to impact. So combining these two, understanding the rate of expansion of this ball in your vision, in your field of vision, and keeping its velocity constant gives you a perfect, dynamic, real-time, evolving plan for catching the ball. So this critical information is readily available, and it's really easy to see how you might start to even accidentally train yourself towards this. This is another one of those local minimums. Those are tractors, right? Like, I am trying to train my system to be able to catch this ball. I'm going to start to, even if I'm just doing things randomly, I'm going to narrow in on this solution. So this is great. I mean, this is the dynamical approach, kind of encapsulated. this constant minute corrections, exploiting something very simple and regular about the way that our system is embedded in the world, right? Like I said, it relies on the way that geometry works from the first person. If we had a strange, like, distributed visual system, it might not work that way. Like, say, being a fly, that kind of thing. So that helps to illustrate embodied cognition. You know, some of the things that my brain are solving, they rely on just the inherent dynamics of the way my body and my eyes and such work. As opposed to doing all of the work up top, we let a lot of the work just be done naturally by the world around us. So our neural systems are always working in tandem with the rest of our bodies to exploit, you know, the simpler solutions. And the idea being that we really shouldn't be separating the two. You know, it just talking about the mind without talking about the body that it inhabits, you leave a lot of things on the table. And that's what the dynamical systems approach is getting at. So let's talk more about human walking. How do I walk? How do you walk? It's so simple, right? We all do it. We all learn to do it because it's so important for us to do as human beings. But are we taking the environment, processing it, solving all those complicated coordination problems, and then executing a program? Or are we just kind of exploiting the way that different angles, muscle tensions, actuators, and all this stuff work together? Is there a springiness to our step because we're exploiting the way gravity works? You know, the answer is, of course, yes, to an extent. But let's talk about how it develops, though. So babies show an interesting U shape in their walking behaviors. In very young infants, they actually make stepping motions. 2 to 8 month old infants, they actually completely stop stepping behaviors. They vanish. And then after 8 months, they start to properly begin to walk. You know, it takes every kid to different time frames, of course. Some less than 8 months and some more, but these are the averages, right? So, okay, what gives here? Why do we start with infant stepping motions and then they stop for a long time and then we start again? Wouldn't it be better for us to just keep trying to walk while we're developing? A standard neural explanation is, well, okay, these are areas that need to mature and able to handle the task of walking, and so they sort of stop working while they are developing something, and then eventually they kick back online. There is an interesting dynamical systems explanation, is that the walking behavior only falls out of our system and our environment when the constraints of our environment and system allow for it. In particular, the organism and the environment. So the task is walking. Why do we sometimes try and why do we sometimes not as we're developing as children? So Thelen and Smith have a set of experiments where they do change these variables and see what is the behavior present or not. So if you hold infants upright in warm water, they will start to mime that motion of walking. And same thing, if you secure them above a mechanical treadmill, their stepping motions will come back. And they'll even adapt to the speed. They're even solving that part of it, right? There is something very primed in their system to be ready to do these behaviors. So, okay, now that's kind of knocking out some of the neural explanation, because the behavior doesn't get pruned away and decay before some other thing, takes over and allows it to come back. You know, a neural area developing and allowing for this behavior. It just wasn't viable based on the constraints. When you change the constraints, the behavior comes flooding right back. So, Thelen and Smith's dynamical systems models involved a few things. At the organism level, the constraints are leg fat and muscle strength, and at the environment level, there is both gravity and inertia. So, stepping behavior reemerges when some of the when this state space is in a particular setting. So let's look at that. Here's the dynamical view. Leg fat is in opposition to muscle strength. That's fine at first. right? The muscle strength is good, and it's more than a leg fat. So very young babies, they pitter patter, right? And you can see the X there on the right. It's sort of this space of good behavior. That you're good to start the walkies, right? Versus if the leg fat eclipses the muscle strength, no more walkies will occur. So this is the first scenario. Fine at first. But then the leg fat, as the baby starts to grow, you know, they're not getting a lot of exercise. They're not doing a lot of tone behaviors, like fitness behaviors, right? They're just a little swaddled bug. Their leg fat starts to exceed their muscle strength. They don't behave in that scenario until eventually muscle strength comes back in babies because they start to do things. They start crawling. They start, you know, they get more active because, heck, they need to, right? They're too curious about the world. So this is showing how this is a good dynamical systems explanation of why this behavior comes out at some times and it doesn't at others. You know, there's more to the picture than this, but this is a good way of looking at, hey, you know, the features of my body determine whether I'm going to behave in certain ways, more so than some deep neural structures phenomenon, right? I wanted to bring up a friend of mine who works in this field and does this kind of dynamical systems modeling. He is John Mathis. He works doing, this was in Austin. He was doing his postdoc, and he looks at the way that our vision, this is a video, I'll play it in a moment, the way that our vision guides our movement through the world, especially over rough terrain. So this is his sort of laser skeleton model. You can see where the model is looking, and we have the benefit of seeing exactly where the footsteps will fall. So we can look at things like, how does what I'm able to take in from the environment determine the kinds of footsteps I'm able to make, right? And using this is an eye tracking and body mechanics study, just capturing the whole dang system so that we can ask questions about everything, right? How's the center of mass? What's going on with the arms? What's going on with the legs, the actuators? You know, this is you can take huge mathematical. Oh, look, even stumbled and caught themselves. You know, you can make a lot of sense of the world of this kind of massive amount of data using this kind of like dynamical systems, large math processing type stuff. So, what do we make of dynamical systems in cognitive science in this realm? We can talk about this as, it's nice because it sidesteps the discussion of how should we characterize all of information processing abilities in the brain. You know, the tensions between a higher level physical symbol explanation versus a much lower level neural explanation. This gets at explaining behavior grabbing from a few more pools than just what does the brain do. Because there's a better question, they think, in what is the brain for? It's for guiding action in the world. So, yeah, how are we connected to the world around us? You know, it's nice. And it's very complex. It has to use this powerful math and lots of data to connect the dots, right? You have to be able to make sense of a lot of mathematical data all at once. But it's also conceptually simpler in a way because it doesn't require a strong, conjecture about how computational processes, what form they take in the mind, right? This might sound familiar. Is this just behaviorism 2.0? Well, sort of. Like I've said before, behaviorism was never wrong. They just didn't. They were very narrowly focused because they wanted to focus on what was observable. Dynamical systems has the same flavor. They want to focus on what is actually observable. And they don't like talking about symbols and representations because you can't pin those down. I'd prefer to be able to talk explicitly about what the data will show and what kinds of complex interactions are there in the data. So they don't deny that there is just like the behaviors, they don't deny that there's complex processes in the brain. Obviously, neuroscience, helps us to understand this stuff. And in fact, the way that a neural network behaves is itself a dynamical system that we can ask similar questions about. So, they're very friendly to the idea that we need to ask deeper questions and that kind of thing. But the focus is on these more broader synergies with the other constraints of the world. So, yeah, not just how the brain works, but how does the brain work in relation to the world? And that's simplified as, what is the brain for? So, takeaway from this whole discussion: information processing is, it successfully explains a lot of cognitive phenomena. But, so do dynamical systems theories here. There's obviously tensions, representations and symbols are key in certain information processing approaches, but they're sort of denied in dynamical systems approaches. But ultimately, we're all getting at the same big question of, how does this thing between my ears even work? So that's it. That's all we're going to get to for dynamical systems theory this time around. And I'll expand it in the future. It's a little bit of a bummer, but time constraints have taken over. The dynamics of this course have been affected by its environmental constraints. So, and its organism constraints. I think we're all a little bit flushed. So, look forward to a couple more lectures. We're nearing the end here. But yeah, take care.